Okay, let's get started. So we are going to continue our discussion on processes and threads and whatnot. Last time, just as a recap, we talked about a process, we talked about processor scheduling, we started talking about threads, and I explained different kinds of threads, kernel level threads, user level threads, and so on. Okay. What we will do today is actually take it from that point on, talk about multiprocessor scheduling and then distributed scheduling. Your question?
Just a question from leftover from last week.
Sure.
So we talked about how lightweight threads are like so great, they have all these benefits, but then they're only used in this one operating system. Have they ever been used since then?
Okay, there's a question about lightweight processes specifically, and that they were used in this one operating system, which was Solaris. Have they been used since then? That's the question. Right. So, so lightweight processes were used in one operating system. They don't exist exactly as they were designed in Solaris and other operating systems, but many of the ideas have carried over. Okay, that's the right way to think about it. All of P threads, if you know what POSIX threads are, those also originated from the same operating system. A lot of the functionality from lightweight processes eventually became P threads. So that is at least one way in which they live on, but not exactly that concept. Okay. So any other questions on this? Okay. So I want to remind everyone not to use laptops and devices. I actually see one student here who is, excuse me, no laptop use in class. Can you shut your laptop? We don't allow laptops in class. Thank you. Okay. So multiprocessor scheduling, that's the first module. Okay. So this is the picture you want to keep in mind. Okay. This is, so the circles at the top are processors. So this is one machine. Okay. We are still talking about one machine, multiple cores or multiple CPUs. Okay. And then you have caches that are present at each of the processors. Okay. The caches are actually going to keep instructions or data. Okay. They are used to speed up the execution of the program. Okay. So that's basically what the caches are. And you might have more than two levels of cache. You might have L1, L2, and L3 cache. That doesn't really matter. The fact that there is a cache associated with each processor is going to be important, as we will see in just a moment. Okay. And then there is memory or RAM. Okay. Memory is actually shared across all of the processors. Okay. A program running on one processor can access any address in memory. Okay. But caches are dedicated to each processor. Okay. So caches are not shared, memory is shared. That's the thing you want to keep in mind. Okay. Now, so what does this have to do with processor scheduling, or specifically multiprocessor scheduling? I'm going to describe two implementations. Okay. And we'll try to understand the differences between the two. Okay, one is a centralized queue implementation, the other is a distributed queue implementation. Okay, in this case, in the first case, we have all of the processors that share a single queue, single ready queue. Okay, that is where all the threads and processes are actually going to be present. Okay, whenever the time slice on any processor is going to end, that processor is going to look at the ready queue and pull a thread or a process from that queue and schedule it. Okay. Now, this is one logical queue. It could be multi-level feedback queue, doesn't matter, but let's just assume there's one queue at the moment. Okay. So that queue is shared across all the processors. Okay. So it's a centralized queue. And at the other end of the spectrum, your multiprocessor scheduling uses a distributed queue, where you have more than one queue in the system. Okay. In the limit, you're going to have one queue per processor. Here you actually show one queue for two processors. But you can think of the step where you actually have one per processor. It doesn't matter. There's more than one queue, okay, and more than one processor, and they are shared. Okay, if you have more than one queue, in this case there are two processors sharing the queue, but you could just have one. Doesn't really matter. So in this case, what is going to happen is that the processes or the threads are going to be part of some queue, one of those queue. Okay, when a processor becomes idle, it's going to look at its local queue, it's not going to look at other queues, and only take the next job in that queue and schedule that for execution. Okay. So these are two different implementations. Let's for a moment try to understand what might be pros and cons of using these two implementations to implement whatever policy you want. The policy doesn't really matter at this point. It could be round robin, for example. Okay. Do you see any different advantages or disadvantages of a centralized queue? Yes.
Well, the centralized queue can't only one thing happen at once, whereas like a distributed queue, you know, like you have levels of priority per queue or stuff like that.
Okay, so in centralized queue only we have levels of priority. Forget priorities for now. Okay, priority scheduling requires a completely different framework. Okay, so in this case we'll just assume that this is a standard round robin scheduler. Okay, so then the question is, what is the centralized queue going to give us or not give us? Yes, you want something? Okay, queue might overflow. Let's assume queue is long. Not going to overflow. Okay, so I mean, potentially yes, but I don't think that is really an issue with the send. That could happen in a distributed queue also. Okay, yes. Okay. So better utilization in the centralized queue. That's what you're trying to say, right? Okay. So think about the following. Okay. Let's say there are n tasks there in the centralized queue. Okay. If I had used the distributed framework, I have to take those n and split them across queues. Same n jobs, but now they're split across queues. Okay. How you split them is going to matter. If the queues are not equally balanced, then some tasks are going to get more CPU time than others because their queue is shorter, so you are getting more round robin time share. Okay. So in a distributed queue, you might have imbalances. In a centralized queue, it's just one queue, so it doesn't really matter. Okay. That's one difference between the two. Anything else? Okay, think about what might happen if the number of processors is large and there is one queue. Yes.
Processors will probably have to access the queue in a synchronous manner, so it would be like a bottleneck. They try to request jobs if there's one queue versus position in queue.
Okay, you had something to add to that?
If that were the case, you can use atomics, right? Like atomic swaps and so forth. So you can have a concurrent queue that is very fast. So centralized queue could still be
Okay. So, yes, you want to add something? Okay. Why would they be idle if there are n processors? There are the same number of processors in both. Okay. So there is more locking contention. Just to reiterate what was said here, as the number of processors, CPUs or cores grows, okay, the centralized queue is a shared data structure. You have to use some synchronization primitive. Standard one is going to be a lock. Okay. So if the time slice on one processor ends, it has to go to the queue to pick a job. So it is going to lock that queue and pick a job. While it is doing that, if another processor becomes idle, it has to at least wait until the previous processor has picked the job and released the lock. Okay. No matter how efficient your synchronization primitives are, okay, as you pointed out, you can get efficient ones. There is still going to be a synchronization overhead. Okay, and that overhead is going to grow as you are actually going to increase the number of processors, because there is going to be lock contention. Okay. You might have very efficient implementation, but there will still be lock contention. In a distributed queue, okay, there will be less contention. In the limit where there is one queue per processor, there is hardly contention at all. Okay, you are basically going to go to your local queue and pull a thread, and that's it. So you don't actually, you are not impacted by the number of processors in the system. Okay. So we talked about imbalance, we talked about lock contention, and we talked about how all of that actually impacts efficiency. Yes, you have something to add?
What's stopping the like centralized system from just like kind of pulling something off the end of the queue, moving it, and then storing it during a lock of the queue, and then reopening the queue so that other processors can inspect what's remaining in the queue, and then the single process can operate on what was pulled out of it?
Okay, so the question is, why can't you make a more funky implementation of the queue where you can actually keep some tasks outside the queue so that a processor can pick that task and not contend for the queue, right? So you take it to the limit, you put one. if 3 processors become idle, 2 of them are going to contend because the first one will take the one that you pulled down, right? So as the number of processors grows, that is not going to scale. Okay, eventually you are going to get contention in the main queue. Question?
Why can't we reverse the order instead of processor pulling up the task from the queue pushes the task to the empty processor, something like that.
Okay, a question is why can't the queue push the task to the empty processor? Whatever you do, whether it's pull or push, you still need synchronization because multiple processors need jobs to be pulled from the queue at the same time. You can only still do only one at a time, and some other processor will have to wait until the previous processor has finished. You can't push 3 things at once. You're still going to push them sequentially, right? Or you can't pull 4 things out at once. You have to do it sequentially. So that's the problem. Okay. Now, having said all this, let's come to the real important part of multiprocessor scheduling, which is all the caches that I showed you on the first slide. I showed them for a reason. Okay. The biggest problem in multiprocessor scheduling is not really necessarily the lock contention or the imbalance. Those are issues that you actually have to deal with. But the bigger problem is something called processor affinity, which arises because there are caches that are not shared across processors or cores. Okay. And here is the problem. Okay. Let's say that processor 1 actually picks up a job and it schedules it, okay, for a time slice. By the time the time slice ends, the caches for that processor would be warm, which means they would have stored instructions or data from that job in the cache. Okay. So now if the time slice ends, then the process goes to the end of the queue, okay, and then eventually it appears at the front and gets scheduled on another processor, a different processor in this case. That processor is going to start with a cold cache because it has not scheduled this task before, so it does not have any data or instructions for that task. It might have instructions and data from other tasks, but that doesn't help this task. So it will start with the cold cache. The first many instructions will all be cache misses. So you will slow down the execution, warm up the cache, okay? And then your time slice ends. You go back to the end of the queue. Next time the same thing happens. You get scheduled on some arbitrary other processors because there is no mapping of tasks to processors in the centralized queue. It's first come, first serve. The processor that becomes idle just pulls the task from the front of the queue and schedules it. It doesn't matter where it was scheduled last. Okay? This is called cache affinity. Okay? Now think about a distributed queue. In particular, think about a distributed queue where there's one queue per processor. Okay? In this case, since that process, once it joins a queue, is going to stay in that same queue. Okay? Next time it gets scheduled, there will still be instructions and data from the previous time slice. So you'll still start with the warm cache. Okay? This can actually have a big performance difference between having cold caches and warm caches. Okay? And so the picture I showed you on the first slide is where this actually is important. So in this case, the caches are not shared. So if the job keeps hopping between processors simply because it's a centralized queue and it keeps getting scheduled on different processors, then you have a problem because every time you start on a new processor, your cache does not have the data that some other processor has. But if you had a single queue per processor, this would not be a problem. Okay, you would actually have taken advantage of the previous time slice where there was a warm cache present. Okay? So the big issue that you have to deal with in multiprocessor scheduling is to respect cache affinities. A cache affinity means a process or a thread has affinity to a processor because that cache actually holds its data. Okay? So this argues that you should actually use distributed scheduling, meaning not a distributed scheduling, distributed queue-based scheduling. Okay? Because that is more likely to respect cache affinities than if you had a centralized queue. Is that clear? Okay, so that actually is the biggest issue that you have to deal with in multiprocessor scheduling, although the other 2 issues I talked about also matter. Okay? So now if you respect cache affinities and started using single queue per core, okay, you are in this distributed queue implementation, you got to now deal with load imbalances. Every once in a while you got to look at all the queues, look at the length and equalize them again so that every process gets its fair share of the CPU time. Okay? If some queues are short and other queues are long, then you have imbalances in the system. Some processors are more utilized than others, or some processes get more CPU time than others, neither of which is a good thing. Okay? So if you try to respect cache affinity, you got to then deal with the queue imbalance problem. Okay, but you don't have the lock contention problem. So this is all a trade-off that you have to deal with. Any questions on this? Okay. So I did mention cache affinity, which is you want to try to schedule that task on the same processor that it was scheduled last. Okay, and so that's one thing. And the second is, even though you might do this, every time you run again, you might not have all of your data and instructions in the cache because there may be many processes in your system. So you want to have larger time slices or larger quantum durations to account for the time where there's some part of its early fraction of the quantum may be all cache misses. So you still get to run once the cache is warmed up for some period of time. So put another way, time slices in multiprocessor systems tend to be longer than the ones that are used in uniprocessor systems, because you have all of these problems of caches and whatnot. Okay. Is that clear? Okay. So now I'm going to talk about one last point on multiprocessor scheduling, and then we'll switch gears to distributed scheduling. Okay. So this is parallel scheduling. Okay. Until now, when we talked about uniprocessor or multiprocessor scheduling, we assumed that processes were independent, threads were independent. Okay. We just picked the one at the front of the queue, and we did not care about what was running on other processors. Okay. Now, if you think of a parallel process, okay, where let's say a process has many threads, or a job has many processes that are coordinating some larger activity, okay, you might not want to schedule them independently. Okay. Because if you schedule them independently, that might actually increase waiting times. And I'll give you a simple example. Okay. Let's say there are two CPUs, okay, A and B, okay, and then there is a process where it has two threads, okay, which is T1 and T2. Okay. Now let us assume that when these threads get scheduled, they also communicate with one another for whatever purposes that the application needs. Okay. So if they are scheduled independently and there are other jobs in the system, when T1 runs on processor A, T2 may not be running on processor B, some other job may be running on processor B. Now if T1 sends a message to T2, it will wait for a reply until the processor B actually runs T2, T2 can receive the message and process it. So the waiting time for T1 has gone up simply because it is waiting for its message to be processed by T2 and waiting for a reply from T2. Okay. Now if you had actually scheduled them as a group as opposed to being independent threads, what you could have done is you could have said these two need to be scheduled together because they communicate, okay, and then if they're scheduled together, this communication will result in less wait times. Okay. So now you're scheduling them as a group, which means T1 and T2 both get scheduled at the same time on processors A and B. Okay. They actually get scheduled in the same time slice. Okay. So in this case, now any coordination, communication can actually execute, be processed without too much waiting, and if they are scheduled independently. Okay. That's a very trivial example that shows you that when you are scheduling parallel applications, where applications consist of many threads or many processes, you shouldn't treat those processes or threads as being independent. You should treat them as being dependent, as being part of one larger group, and schedule that entire group at once, not schedule individual thread and all. Okay. This simple idea is called gang scheduling. Okay. You schedule a gang of processes. Okay. So now you are not having one processor making independent decisions from other processors. There is a more global scheduler that decides what should run together on all the processors. Okay. And you schedule this entire parallel application all at once. Is that clear what gang scheduling means? So this is a very specialized CPU scheduling algorithm. It's only used for scheduling parallel jobs. You wouldn't ever use it in a general purpose operating system. Okay. You wouldn't use it on your Mac or Windows because you have many processes. They may be all actually independent, so it doesn't make sense. Okay. You don't want your web browser and your email to be scheduled together because there is no reason for it to be. They should be scheduled independently. Okay. But if you are running specialized parallel applications, scientific jobs that are parallel, then this makes sense. So it is only used in special purpose multiprocessors that are designed specifically to execute parallel applications. Okay. Is that clear? Any questions on this? Yes.
Is there no concept of having a group
Okay, the question is there a general purpose scheduling that you would normally run on a parallel machine and it would switch to gang scheduling only when there's a parallel application? That's your question. So I suppose you could do that. You could actually say, I'm going to run a parallel job, so switch to gang scheduling mode, otherwise you just do normal CPU scheduling as you would do. That is certainly possible. I don't see any reason, technical reason why that shouldn't be the case. Having said that, the machines that gang schedulers run on are so specialized you would not run general purpose applications. They are specifically designed, they have hardware that is specifically designed to run parallel jobs. So the kinds of jobs you see are mostly of these kinds, so it makes sense to just have the scheduling algorithm be gang schedulers. Okay. Any other questions? Okay. So we are actually done with module 1. So we are done with multiprocessor scheduling. Okay. Now we are actually going to get to distributed scheduling. This is really where we wanted to spend more time on, because this is a course on distributed system. So we've done uniprocessor, we've done multiprocessor. Those are still single machine schedulers. Okay, because so there is one processor or more than one, it's still happening inside one machine. Okay, now we are going to look at how do you schedule jobs across machines. Okay, that brings us to this notion of distributed scheduling. Okay. Now, to understand what is being said on this slide, I am going to start with an example, okay, of distributed scheduling. So let's assume that there are n machines, n workstations or n servers in the system. Okay. So let's assume a new application or a process arrives at one of the machines. Okay. Normally that operating system would just schedule that job locally. It would just run it on the machine where the user submitted the job. Okay. Now in distributed scheduling, we also have an additional degree of flexibility, which says that even though the user actually typed the command or submitted the job on machine I, the system may actually decide to execute this job on machine J, on a different machine from where it was submitted, and then bring back the results. Okay. That is what we will call distributed scheduling. You are now taking jobs that are arriving at one machine, but running them somewhere else in the system. Okay. And the question we want to ask is, where does this actually give us benefit? Why would you want to do this? Does it make sense? Okay. Does it actually give us any real benefit, or just running jobs locally, which is what you would normally do using your uniprocessor or multiprocessor schedulers. Okay. So to understand whether such distributed scheduling makes sense, we are going to take two scenarios. We are going to take a lightly utilized system and a heavily utilized system and ask the question, can we actually take advantage of distributed scheduling? Okay. So let's take the first case. The system as a whole is lightly utilized. Lightly utilized means that there are few jobs in the system to begin with. Okay. So now let's say job arrives at machine I. Okay, we should ask, does it actually make sense to run it somewhere else, or should you run it locally? What do you think? Yes.
One aspect to consider is just the amount of data you might have to
Okay, so you are talking about data. I'm not even going into what kind of job it is. Okay. Yes, if you move the job, you might have to move its data and all of that. That we'll get to later. I'm simply asking, it's a lightly loaded system. New job arrives. Does it make sense to run it locally, or should you actually try to run it on some other machine? Okay, you have something to say? Yeah.
I was just going to say, probably running it locally makes sense if it's not being used heavily.
Yes, right. So the point is, if it's lightly loaded, that means there's hardly anything running on any of the machines. If a new job comes, you can just run it on that machine. Why would you run it anywhere else? You have enough resources on that machine to run it. Okay. So in this scenario, distributed scheduling is not going to buy you much, because you can get all of the resources that the job needs locally. There's no real reason to move it anywhere else. Okay. It's going to get the same performance locally, because there's nothing else running with high probability. It's all probabilistic, right? So that's one side of the story. Now let's look at a heavily utilized system. Okay. Most machines are heavily utilized. There are lots of jobs running on all the machines with high probability. Okay. Now a new job actually arrives at machine I. So you should ask, does it make sense to run it somewhere else? Does it? Yes, right? Because this machine is heavily loaded. Maybe you should find some other machine where there are resources for this to run this job, because this is going to make this machine even more loaded if you run it locally. Okay? So you say, okay, I think we should use distributed scheduling and run it somewhere else. Okay? But where would you run it? All machines are loaded. This is a heavily utilized system. Okay, you can pick the machine least loaded, but if the least loaded machine is at 95% capacity and this machine is at 97% capacity, does it buy you a whole lot? Yes? Okay, machine may free up, but I'm saying at this moment nothing is available, right? This is heavily loaded. You can make the job wait, that's a different problem. Right? So what they should tell you is, in a lightly loaded system there is no benefit of moving a job because you have enough resources locally. In a heavily loaded system, you desperately want to move that job somewhere else, but there are no resources available in the system for you to run that job because every machine is loaded. Right? So then you should say, why should we talk about this topic at all? There's no point in doing distributed scheduling. Right? Because I just argued that it doesn't make sense when it's lightly loaded, doesn't make sense when it's heavily loaded. Yes, you have something to. Okay, so that's a good point. So you should say, well, why should it only be at those two extremes? Why can't it be moderately loaded? Right? So now let's take the moderately loaded system, okay? Which means that it could mean one of two things. It could mean that there are machines that are somewhat utilized, or there are some machines that are more heavily utilized than others, but on average the utilization may be somewhere in between light and heavy. Okay? So now in this case, if a job arrives at machine I, and that machine I just happens to be less lightly loaded than some of the other machines, then you run it locally. There's nothing to do. But on the other hand, if that happens to be more heavily loaded than the average machine, then you might still find some other machine to run that job because it's moderately loaded. Doesn't mean everything is 50%. Maybe some may be 20, some may be 70. On average, you may be somewhere in between. Okay? So this is a scenario where you are actually going to get benefits for distributed scheduling. Okay? So you have to be very clear. This technique is not going to give you benefits at all times. It's only going to give you benefits in certain parts of where the system utilization could be between lightly loaded and heavily loaded, somewhere in between. Okay? That is essentially what this curve shows you. Okay? And that curve is actually asking the following question. It's saying, what's the probability that there is at least one system idle in one machine idle in the system, and then there is one job waiting to run? Okay? That's the same discussion we just had, okay? Asked in a more technical way. Okay? So system idle essentially means that there is some machine that has more resources, that it can actually run more jobs than it is currently running. That's what that means. Okay? Job waiting means the job has arrived at a machine that's actually heavily loaded, so it's just waiting to run. Okay? You are going to get benefits of distributed scheduling when both of those events are simultaneously true. Okay? Job arrives at a machine and it has to wait because the machine is loaded, but there is some other machine in the system that actually is lightly loaded or has no load. So you can move that job there and run it. Okay? So distributed scheduling makes sense only when both of those events are true. Okay? And that's what the probability distribution of both of those events being true looks like. When the system is lightly loaded, okay, the probability of this event, okay, being true is very high because all machines are idle essentially. Okay? But probability that the job waiting is almost zero because no job has to wait. So you take the product of those two, you get low probability. Okay? Because only one event is going to be true most of the time, the other is not. Okay? In a heavily loaded system, the opposite is true. Okay? The probability that the job waiting is high because every job when it arrives, it is actually going to arrive at a heavily loaded system, so you have to wait. Okay? the probability that there's an idle machine in the system is almost 0. Okay? You take the product of the two, you are going to get low probability. So as you go from utilization of 0, average utilization, to 1, the probability of those two events being together rises and falls, and this is the region in the middle where we are going to get benefits. Okay? Because here there's no point moving the job, there are local resources. Here there are no resources even though you want to move the job. Okay? In the middle you can actually do both. Okay? You have a job to move and there's a machine to take that job. Okay, yes, question? Okay. X-axis is system utilization. Utilization goes from 0 to 1, which means 0% utilized on average to 100% utilized. Y-axis is the probability distribution. It's just plotting the probability distribution of this, these two events being true together. Okay, yes, question?
What are there are 3 lines.
Okay, there are 3 lines that those just are different parameters of the system which you can ignore for now. Okay, they just say what arrival rate and what rate they complete. We don't really need to go into it. Okay. Any other questions somebody had? Sorry?
Is the graph scaled?
The,
Can do above, it can't do above 0.5.
no, the probability,
Mu into 1 minus mu naught
no, the probability that the system is idle is high, right? And the probability that job waiting can also be high. So in the middle you can actually get high. It doesn't have to be 1, but it can be high. Okay. Any other questions? Okay. So now that we have thought carefully about does this even make sense, and we convince ourselves there are some cases where it makes sense, you got to ask where are we going to use it, how are we going to implement distributed scheduling. That's what we are going to talk about, but this one actually, just this slide just simply summarizes all the discussion we had, which is at high utilization there is little benefit to distributed scheduling. At low utilization there's hardly a job waiting, so really nothing to do. So you want to basically be in the middle. Okay? Now we want to ask when we design a distributed scheduling policy, which we will look at next, ask what is it that we want to minimize. You could say let's just minimize things like waiting time or response time. That's the usual metric. Okay, we also need some measure of load, because we said on what basis are you going to decide is the machine loaded, not loaded, etc. So you got to figure out what is the definition of load. It could be something like CPU utilization. It could be something like the queue length, okay, how many jobs are actually in the run queue. Okay, we actually have a queue where jobs queue up and the scheduler picks them. Okay, so you can pick whatever metric, but you got to pick a metric that is some characteristic of load. Is that clear? And we'll see which ones to pick in just a moment. Okay. So with that, let's actually talk about some design issues. So for load, we are simply going to use queue length. Okay, we are not, CPU utilization could be used, but it doesn't really matter. Okay, we are going to study 3 types of techniques or policies. A static policy, which means that the decision on what to do is actually predetermined, it's hardwired in the system. Okay, the more interesting ones are the dynamic policy, which actually decides dynamically what to do based on the current load on different machines in the system. And we'll pick an adaptive policy where the policy itself changes based on what is happening in the system. Okay? In one regime you might use one policy, in another regime you might pick a different policy, and we'll see examples of all of those. Okay? We can also ask whether the scheduler should be preemptive or non-preemptive. Okay? Preemptive scheduler says once the job has started executing, can I preempt it and move it somewhere else? Okay? Non-preemptive says once you start a job, and when the job arrives, you can pick which machine to run it on. Once it starts running, you are not going to move it around. That's where it stays until it finishes. Okay? Your question there, yes.
You talked about adaptive.
Yes.
Adaptive policy. Are you saying that it's choosing amongst a bunch of static policies?
Yes. Adaptive policy means you can pick between one of 2 dynamic policies or 1 or 2 static policies. You can change the policy itself based on what's happening in the system. Okay. Any other questions here? Okay. So preemptive versus non-preemptive. Centralized versus decentralized simply says whether the queues are centralized or not. We don't really worry about that too much here. Okay. But we did talk about that in the multiprocessor scale. The last thing which is important, but I won't go into that too much here, is that you want the system to be stable. Okay. What stable means is you don't want a job to arrive. Okay. Machine I says I don't want it. sends it off to J. Machine J says, I don't want it either, and you send it off to some other machine. It just keeps hopping around, and then lots of processes are being shuffled around. Nothing is actually getting done. Okay? So you don't want to have that scenario. Okay? This typically happens when the system utilization, the arrival rate is such that it is approaching system capacity. Okay? That's actually queuing theory result. And since we don't do queuing theory in this class, I'm not going to go into lambda and mu and so on. Lambda is the arrival rate, mu is the utilization. Typically, queues become unstable when the arrival rate actually is such that your system gets heavily utilized, and then queues start building up. Okay? And when queues start building up, you might start transferring jobs, and when jobs start moving around, nobody wants to accept them, they might just start hopping in the system. You don't want that kind of scenario. If the system is heavily loaded, you just want to say the job is just going to run here. Doesn't matter whether the machine is loaded or not, and at least it gets to run. You don't just keep sending it from one machine to another. So you don't want that kind of policy. You don't want an unstable policy that's not even able to decide which machine should run this job. Okay? Now we can start thinking of policies, and you will see some policies that might have better properties than others. Okay? And I'm going to talk about, when I say a scheduling, distributed scheduling policy, it's going to have 4 components to it. Okay? The first component is transfer policy, okay, which says when to transfer a process. When should the process be moved from machine I to machine J? Okay, we are going to use simple threshold base, as we'll see on the next slide. Okay. Then the policy has a selection part, which says which process. I've decided I want to move some work from this machine to some other machine. Which process should I move? Okay. And typically we would like to move new processes that have just arrived, haven't started executing, to existing processes, because that's more expensive and more complicated, as we'll see. Okay. Location policy says now which machine should take this work, extra work. Okay. So, and we'll see how to figure out, is it the least loaded, it's some other approach, we'll see that. And the information policy says what information should the scheduler keep to make all of those decisions in the right way. Okay, what do you need to know about the system, whether it's this machine or other machines. Okay? And we'll see that that can also be different depending on the policy. So let's take real policies, and you'll see how those things map to that policy. So the first one is called sender initiated. Okay, these are now actual distributed schedulers. Okay? This is called sender initiated. As the name suggests, okay, the sender is the one that is going to move the job around. Sender meaning that's the machine that the job arrived, that's going to be called the sender. Okay? So the transfer policy simply says if a new job arrives in the system, okay, you are going to look at the number of currently executing jobs in the system, which is n. Okay? We will keep a threshold. If n goes above threshold, we say that it's time to start moving some jobs to some other machines. Okay? So, and in this case, you just have a queue-based threshold. You can say this machine can execute 15 jobs concurrently. If the 16th job arrives, you say let's move it somewhere else. Okay? The machine is loaded. Okay? That's basically going to be our transfer policy. It says when do I trigger moving of jobs. Okay? When you exceed the threshold T. T is a parameter for this policy. Okay? Selection policy says now that the load has exceeded T, okay, which job should I move? So some job has, there are n plus 1, T plus 1 jobs. Okay? You have to move one job out so that you are actually at T or below. Which one should I move? Okay? By definition, we will pick the newly arrived process because that process hasn't executed yet. The user has simply typed a command. Okay? You haven't even set up the process. So if you just execute that command elsewhere, that's the easiest thing to do. Okay? If you had an actual process and you wanted to move it, that's very complicated. That requires something called process migration, which we will come to. Okay? If you just start executing this command somewhere else, that's your easiest thing. So that's what we mean by newly arrived process. So that's the one type of jobs we prefer to move. Okay? Location policy says where should you move this job. Okay? There are many ways to make that decision. First one says random. Okay? Toss a coin, move that job to machine I. Okay? You pick it randomly. You have no information about what's actually happening on machine I. Okay? That's one approach. Okay? Or you could say I am going to actually poll the node sequentially. So I go to node 1 saying what's your load. Is it above or below T? If it's below T, I say, okay, you take the job. Okay? If it's above T, you move to the next one. So you are going to sequentially poll all of them until you find one machine that has a load less than the threshold, and you say that machine is not loaded by definition, its load is less than a threshold, and it can take this job, and you give it. Okay? So you are doing sequential polling. Okay? Not the best thing to do, because if you have lots of machines, you are going to keep polling sequentially, but that's one way. Okay? You could also poll the machines in parallel, saying you send a broadcast query to all the machines, send them, ask them for their load, they all send your load, you can pick the least loaded. Okay? This is how you can do the least loaded, because you got to ask all the machines what the load is. Okay? Then you pick the one with the least n in this case, and that's the machine that's going to get the job. Okay? It's a very simple policy, but it should now tell you that we broke down the distributed scheduling algorithm into smaller pieces, how to pick a job, when to pick a job, which machine to choose, and what information do you need to keep. In this case, our information policy is trivial. We don't keep any information. We go and look for it on demand by polling, because the information you need is the load on other machines. Okay, we are just polling on the fly, and then we get that information, make the decision. Okay. Questions on this? Is this clear? Okay. So now we are going to flip it and talk about receiver initiated, which is the exact opposite. Okay, you have a question? Yes.
So the information policy is demand-driven.
Information policy is going to be on demand. Yes. You just ask whenever you need. You don't keep load. You could have queried load periodically, kept load tables. You don't do that then. Okay. Receiver initiated is the opposite. In this case, you again have a threshold T. If the load on the machine goes below T, it becomes a receiver. It says, I can go look for more work. Okay? So you go and ask other machine, do you have a job that I can take over for you? Okay, that's what a receiver means. You are willing to receive jobs. So you go ask hunting for work in the system. Is that clear? In the sender initiated, if a machine is loaded, it tries to offload work to some other machine. In receiver initiated, if you are lightly loaded, you go and look for work to take on. Okay? So in this case, if a process departs on a machine and the load goes below tau or T, which is our threshold, you become a receiver. Okay? And then you go and ask for a job. Okay? Again, selection policy is you prefer to take a newly arrived process so you can just execute it from the beginning. But you could, of course, do process migration if need be. Okay? We'll come to that. Okay? So we prefer always to take newly arrived processes. Okay? The location policy is the same. Okay, you are going to either go randomly ask a machine and do you have any work. If it says yes, you take the work. Otherwise, you keep polling randomly until you find a machine that has high load and is willing to send you jobs. Okay? Or you can poll sequentially and find the first machine that has load greater than T, you ask for it. Okay? Or you can poll them all in parallel and ask the most heavily loaded machine saying, give me a job. Okay, it's the exact opposite of whatever we did in the sender initiated. Is this clear? Any questions here? Yes.
Transfer policy says if departing process causes load less than T, so only then does the machine look for jobs, or just because it's less than T, it looks for jobs?
Right. So if the load hasn't even exceeded T, you are a receiver. You can still look for a job. Okay, but if you already had enough processes to run, the first time it drops below T, again you become a receiver. So basically it is saying if your load is less than T, you are a receiver. You can go look for a job. Any other questions? Okay. Now we look at, here's a symmetric policy. This is an example of an adaptive policy, okay, which is going to combine sender initiated and receiver initiated. Yes, your question. Yes. Right. So in both of these, I have not talked about the information policy, because information says what information do I need to keep. In both of those cases, we are polling on the fly, so we don't keep any information a priori. But we'll see actual systems don't do that. They keep information. These are very trivial policies. We're just starting very simple. Okay. Okay. Here's one symmetric policy. Okay. This combines both sender and receiver initiated, saying why do one or the other, why not have both? Okay. If you are lightly loaded, you go around looking for work. If you are heavily loaded, you go around trying to offload work, and maybe you can have both of these things running at the same time. There is no reason to pick one or the other. Okay. So nodes could be in one of three categories. Okay. There are two thresholds now, a high threshold, okay, above which you become a sender, a low threshold below which you become a receiver, and in the middle you are moderately loaded, you are neither offloading work nor taking work. Okay. So you could be in one of three categories. If you are lightly loaded, which means you are below the low threshold, you are going to look for jobs to take on. If you are in the middle, you said there's nothing to do, neither have to send anything nor take anything on. If you are heavily loaded, you look for other nodes to take on some jobs. Okay. So depending on your load, whether you are in above the high threshold, in the middle or below the threshold, you could be a receiver, sender, or neither. Okay. So you can be neither, which means you don't do anything at all, you just schedule locally. Okay. So that's basically how you are going to decide whether a node becomes sender or receiver initiated. And if you become sender initiated, you run the sender initiated policy we described. If you become a receiver, you run the receiver initiated policy we described. If you are in the middle, you do nothing. Okay. Is that clear? Okay. So now, that is why the policy is adaptive, because the role of a node is actually whether it's sender or receiver or neither is going to change, and you are picking between two policies depending on whether sender or receiver. Right. So now you could say what is the information. So selection will always assume is I try to pick a newly arrived process, so that's always the case. So then you could say how do I decide where to send jobs or where to take jobs on. Again, you can always use polling. You can send a broadcast message saying send me your load information. Based on that, you can pick the most lightly loaded lightly loaded node, send it a job, take the most heavily loaded node and accept a job from it, or any other policy. You can use randomize, doesn't really matter, but you can actually just use polling based approaches. That's the simplest one. Any questions on this? It is called symmetric, yes.
In case of high utilization, the system will try to send the process to another node, but all the systems are at high utilization. So how will it work in that case?
Okay. Question is, if it's high utilization, you are going to try to offload work, but if all machines are heavily utilized, you can't find any node to offload work. Right? If the entire system as a whole, which is the whole collection of machines, are all heavily utilized, then what you said is true. What this is saying is what is happening on each node, which is independent of what's happening on other nodes. So as we already discussed, distributed scheduling only makes sense when you are moderately utilized as a system. Okay? So we are assuming we are in that regime. What do you mean by moderately utilized is some nodes may be heavily utilized, some may be lightly utilized, or so you are somewhere in between. Okay, if all of them are heavily utilized, obviously there's nothing you can do, as we discussed already. Yes.
Isn't there like a communication overhead in this type of policy?
Yes. So the question is, isn't there communication overhead? There are actually multiple types of overheads, one of which is a communication overhead. If you use this kind of information policy where on demand you go poll, okay, that might be extremely wasteful. Okay? Because you might have 1,000 machines in your cluster. You're asking all 1,000 machines periodically what the load is. Okay? Much better approach is every 1 minute you basically broadcast your load, so you just keep listening for this and keep a table. Every time, or not even 1 minute, every time your load changes significantly, you broadcast information. There are many other approaches that will be a lot more efficient communication-wise. At the moment, we are not trying to strive for efficiency. We're just trying to understand how to design a policy that makes some sense. It's not the best policy you can design, obviously. There are much better things you can do. Yes?
And are policies always node-based, or can they also be system-based?
Okay. Can policies be node-based or system-based? At the moment, we have actually talked about a fully distributed policy where depending on whether you become a receiver or a sender, you take action. We will soon see coordinator-based policy. There's a coordinator that's making these decisions, saying you are a sender, you are a receiver, this job should move from here to here. Those are distributed scheduler, but there's a centralized coordinator. Okay. In this case, there is no coordinator. Every node is doing what it needs to do based on whether it's a sender or a receiver. Okay. But we'll see other approaches in just a moment. Yes.
So how does it define the average load? It's the average load of all the nodes.
How does the system define, what do you mean by how does it?
Average load. So the
Okay.
average load is predefined or it's
No, so I think there are only two parameters, a low threshold and high threshold. Anything in between is just assumed to be moderate load. Okay? So if you're above the high, you are heavily loaded. That's a parameter you pick, saying if you are above 80%, you are heavily loaded. If you are below 20%, you are lightly loaded. Everything in between, you are fine. Right? So that's what you are going to do. Any other questions here? Yes. Okay, how do you choose the parameter? That's a configurable parameter. I think that's the policy doesn't care. Once you pick the parameters, it's going to decide. You can be more aggressive or less aggressive based on how you set the threshold. The thresholds are not chosen adaptively. If the question is, can the thresholds are actually input parameters, you're not going to change them. Okay? What you do based on the threshold will change depending on your own load. Okay. So with that background, I'm going to now actually talk about real systems that have implemented these schedulers. Okay? We talked about some very simple concepts, sender initiated, receiver initiated, and as you can imagine, they're really straightforward. Now we can take a look at actual systems and see how they implement these actual distributed schedulers in practice. Okay, we are going to start with very early ones that actually resemble sender and receiver initiated, and then we will build from there and look at some more modern ones. Okay. First one is called the V system. It's an operating system that was designed in Stanford maybe 20, 30 years ago now, several decades ago. It actually implemented a distributed scheduler. You had a cluster of workstations. The workstations had their local CPU scheduler, but they also ran a distributed scheduler. If the machine got loaded or lightly loaded, you could actually offload work or take work on. Okay? So here the information policy was what is called state change based. If there was significant change in load, you would broadcast your load, okay, to all the other nodes. And so nodes would also listen to this broadcast, and they would keep a load table. So they would say what is the load on system I is already stored in the table based on the most recent information I have received. Okay. Now keep in mind that whenever you construct these load tables, it will almost always have some outdated information. Okay. Unless you are going to broadcast your load changes very frequently, okay, you are going to have the most recent broadcast from node I, which says that is the current load on I, but since then the load may have changed. So if you make decisions solely based on load tables, you might find that the decision is actually incorrect because the table has outdated information. This is why the simple policies did on-demand pooling, which means you always get the most accurate load. You are asking for the current load, not something that was true 5 minutes ago when it was broadcast, for example. Okay? But be that as it may, the communication overhead of these kinds of approaches is much lower because you basically say every once in a while, I'm going to tell everyone this is my current load. So then they use that information to make whatever decisions they need to make. Okay? So in this case, M least loaded nodes are receivers. M is a configurable parameter. The others are senders. So there is no in between here. Okay? You take the most heavily loaded machines, not the most heavily loaded, the most lightly loaded machines, the M of them, they become receivers. Okay? Everything else is a sender. Okay? So now these M machines are going to go and look for work. Okay. So it's a sender initiated policy with new job selection. Okay. And then the location policy is you're actually going to take the load table that you have, okay, pick the M least loaded ones, and then you actually still poll on demand because that information may be out of date. Okay. So you're going to probe a random receiver from M because you don't know the actual load, you just know the last reported load, which may not be the current load. So you use that load table to actually not poll everyone, but just selectively poll the M least loaded one and say, are you still a receiver? If so, you are going to say, here, take a job. Okay. So they basically optimize how you go about finding a machine to take on a job. Rather than polling everyone at random, you periodically broadcast load information. Then you keep a table. You take the M least loaded machines, and those are the only ones you will poll, not every other machine. Okay? And if you find one out of those m that is willing to take your job, you are done. Is that clear? Yes. So somebody had a hand up. Okay. So that's what this Sprite operating system did. No, not Sprite, V operating system. Sprite is the other one we are going to look at, which is a competing operating system that was developed at Berkeley around the same time V operating system was designed. These were both research projects. Okay, they did not end up in commercial implementation, but they actually built real systems that implemented these policies, and it was used in some scenarios by people, but never actually became commercial product. Okay. But now let's talk about Sprite. Okay. You will see some things are very similar. Okay. In the case of Sprite, it also assumed a workstation environment. It assumed that every user had a desktop or a workstation. Okay. And the assumption was the user owned their desktop, which means they actually controlled what ran on their desktop. Okay. Except for when they were not at their desktop, then they didn't have any control. If you sit on your desktop, you are doing work. Okay. You don't want some random machine starting to send jobs to your machine and it gets loaded, because you are trying to do your work. Okay. So when you are actively using your machine, nothing else other than your jobs run on it. Okay. That's what is meant by owner is king. Okay. But if you are not at your machine is just running and it's sitting there, then it's fair game for some other machine to send it jobs. Is that clear? Okay. So that's the philosophy that they used. So it said so basically they said, so how do you detect an idle machine? They said if there's no keyboard or mouse activity for 30 seconds, okay, half a minute goes by, you are not moved your mouse, you are not typed on your keyboard, and the number of active processes on your machine is less than the number of processors, okay, which means that there is at least one processor idle. Okay, that basically says there's an idle processor and you have not used your machine for half a minute, then your machine is willing to start accepting jobs. It becomes a receiver. Okay. So in this case, essentially the selection policies is chosen by the user. The workstation is going to be the sender as soon as you submit a job. Okay. And there is a centralized coordinator. The coordinator, sender is going to say, I have a job to run. You ask the coordinator, where should I run it? Okay. The coordinator is going to keep track of when node becomes a receiver, that receiver actually contacts the coordinator saying, I am a receiver, do you have a job? Okay. So there's a centralized node that knows all the receivers in the system. These are all machines that have not been used by their users for at least half a minute, and they have at least one processor idle. Okay. So the coordinator has a list. As soon as there's a sender, you ask the coordinator says, go run it on machine I. Okay. So then you run the job on machine I. Is that clear? Okay. So now if you go for lunch, your machine is just running there, it might start taking someone else's job. Okay. So now you say, I come back from lunch and there are 4 jobs running on my machine, I can't do my work because I need to run my jobs. What should be done? Okay. So their philosophy was owner is king. Okay. The moment you come back to your workstation, okay, it is given back to you. If some foreign job is running, then it's booted out immediately saying you are done. Okay. User needs their machine back. Okay. So you are only harvesting idle cycles. Idle cycles are cycles that are on the machine when the user is not actively using that machine. Okay. So from a user's perspective, they say no difference at all. Whenever they are sitting on their desk working on their machine, it looks exactly like they are the only ones using it. When you are not at the machine, do you really mind if some other job runs? You shouldn't, because as soon as you come back, you are given your machine back. Okay. Yes, your question there.
Couldn't they have done something like lower the priority of the jobs that come in while you're on your machine?
Sure. So the question is, couldn't you have lowered the priority of the foreign jobs, or no, I shouldn't say foreign because I didn't define that term, but jobs that you received from other machine. You could have done that, but their philosophy was your machine should look no different, and you should only lend your resources when you're really not using your machine actively. So in this case, they took an extreme step which says, if you are back at your machine, all jobs that were sent to it from other machines have to be suspended and moved somewhere else. Okay. Now what they should tell you is this operating system actually needs to do a lot more things than other policies we have seen. In particular, it needs something called process migration, which is you take a job or a process that's actively running and you suspend it, you move it somewhere else, and it continues execution as if it always executed on that other machine. Okay? We haven't seen how to do that yet. In fact, most operating systems even today don't actually have that feature because it is fairly complicated to implement. It's one thing to say, I sent in a Python job, I just actually start executing it somewhere else. It's a whole different thing to say there's a job running, I suspend it, I move it state somewhere else, and I resume execution. That's a lot more complicated to do. Okay, yes, question.
Are these jobs like exclusively CPU, or would you like expect to see like changes to your file system?
Okay, the question is, are the jobs exclusively CPU, or can they do I/O? They can read or write file. So that depends on many of these scenario systems. They make different assumptions actually. Okay, but by and large, the jobs are allowed to do I/O. They can basically, they're batch jobs. They can read some data, compute, and write some data out, which means also that there has to be a file system that's shared across machines. Because you don't want to write your data on somebody else's disk and then you move away, and then how do you get your results, right? So you want it on some centralized server. So there's always a file system involved, which we ignored so far. Yes.
So, I mean, it sounds like the idea of this is that like a researcher, like you said, a researcher goes out to lunch and their CPU cycles get used. But
Right.
like, wouldn't the common thing that would happen is everyone goes out to lunch and everyone comes back and there's nowhere to send all these processes that are running?
Okay, so question is, everyone goes to lunch at the same time, nobody is doing work. No, so you could actually have a queue of batch jobs, which are not jobs. They could just be queued up. It's not like you're sitting when somebody else is going at lunch and submitting jobs. You could just have these jobs that are just sitting there, and every time there's an idle machine, it runs. When the idle machine becomes not idle, then it gets suspended. It goes back to the queue, then it resumes execution somewhere else, and so on. Okay?
Presumably because it could do the process migration, it would just be able to suspend it and wait some.
Right. Because you can do process migration, you can actually keep it in suspended state and resume at a later point. It doesn't have to resume immediately. If you could, that's better, but it doesn't have to. Right? Any other questions here? Yes.
Where would you actually even store the jobs then that you have to migrate if there is a machine to migrate?
Okay, where would you store the job? So I don't have too much on process migration yet, but I do have a little bit. Okay, so this is how Sprite would do process migration. Okay, so the first operating system 30 years ago, but first one that actually came up with this idea of we can actually take a process and move it somewhere else. Right? Think about it. You actually have an application running. Maybe it's a mail client, you're running Python job. It actually just moves somewhere else and continues execution. You're not killing it and restarting it. That's not what we mean by migration. You're just moving it as is and it just starts executing somewhere else. That's fairly complicated to implement. Okay? Now, the central thing that you need is a shared file system. Okay? Because what you're going to do is, if you want to suspend a job, what you will do, this is the canonical thing you'll do. You'll take its memory contents. Okay? First, you'll stop executing it, so memory doesn't change anymore. Okay? You'll take all of its memory contents, you'll write it out to disk. Take all of the registers, you write it out to disk. Okay? Now you saved that job. Okay? Now in principle, not in practice, in principle, you can take those memory contents and load them on some other machine. You can take those register values, load them on the other machine, and then you should be able to resume execution of that job. Okay? Because you basically restored the memory content and you basically restarted execution. But to do that, you have to start a blank process on that machine and say this is the memory contents of what you need to have in that process, and reinstantiate that process as it looked on that, because not a new process. It's an existing process that you're moving over. Okay, so you need to do extra work in order to set up a process that's not a new process, but it's just moved to this. It's new to that machine, but it's not new to the system. Okay? So that is essentially what you're going to do at a high level. You will basically do what is called state transfer. Okay? You will take the memory contents, you'll write it out to disk, okay? And then you will essentially assume that either that disk is accessible somewhere else. So that also means by the page tables, everything else has to be written out. And then you will resume execution and you will bring it on demand. Okay? The big problem here is when you have that process accessing external resources. If purely CPU bound process, this is not that hard to implement. Okay? You can do it. But if you had open files. Okay, it was actually accessing a file on that local disk. Now you moved it here. So that file is not going to be accessible on this disk. It was accessible somewhere else. What do you do? Okay. Even more complicated. What if I had open network connections? There's actually a server application that is accepting requests. You just move it over, it's not going to work because network connections are bound to IP addresses. IP address is local to a machine. The IP address is not going to move even if you move the process. Okay. So process migration is complicated by external resources that a process accesses, which could be files, network sockets, and many other things. Okay. Unless you actually have a seamless way of making those resources accessible on the new machine, by and large this is not going to work. Okay. This is why it's very complicated even today. Okay. But assuming that this is simply a CPU bound process that's not doing much I/O or doesn't have network connections, you could do this and make it work. If it's a batch job, by and large that's all you may do. Okay. You are just sending some maybe jobs to do some inference if you're running a machine learning job, for example. All it does is it might read some files, and if the files are on a network file system, you take that and you basically produce a result. That's all it is doing. That may be okay. If you start writing to local disk, then you better move the data also, otherwise it's not going to work. Okay. So that's process migration in Sprite. So as the first operating system do it, it came with restrictions. You couldn't migrate any arbitrary process, but you could migrate certain types of processes, which was still in advance. It still allowed us to do distributed scheduling. Okay. It still allowed them to return the machine back to the user. Okay. The only other way they would have to return the machine is simply kill the job and then restart it somewhere else, which means everything you've done so far is all wasted. Right. So this is a much better approach. It allows you to migrate the process and whatnot. Okay. Any questions on this? We'll come back to other more modern ways of doing migration, but this was the first operating system that allowed you to migrate processes. Okay. Case study 3 is a different take at distributed scheduling. This is called volunteer computing. So in this case, there are users who are basically volunteering their machine to take on work. Okay. And so I don't know if you've heard of things like SETI at home. Okay. That was a very old project where there were astronomers who wanted to look for extraterrestrial life in radio signals captured by radio telescopes. Okay. So there's a lot of data. You're just looking for a small amount of signal with lot of noise. You need lots of machines to run this. Okay. And it's very expensive to get large clusters. So they said, why not actually ask users who are sitting anywhere in the world to contribute a little bit of their CPU time. Okay. So the way this works typically is you download an application, okay, that essentially acts as a screensaver. Okay. So whenever your screensaver turns on, this special screensaver is going to contact some central server somewhere saying, this machine is idle, please send me some work. Okay. So there's a central node which has lots and lots of little jobs. Okay. You take a big job and you make lots of little jobs out of it. And whenever some machine somewhere on the internet says send me a job, you send it a little bit of data saying go run this computation, send the results back. Okay. So you basically take your task and chop it up into small pieces. Large scale data processing is a good example where it's embarrassingly parallel. That you can make very small chunks of data and process little bits of data. And if you have lots of machines, you still get a lot of parallelism. Okay. So essentially this scenario is one where users are actively saying, please use my machine for some task. Okay. Now since SETI at home, this has become a more mature project. Now it runs under this umbrella of BOINC, which is Berkeley Open something network computing. I forget what I means. So this is a project where you have lots of scientists saying, let's do cancer research. Need to process a lot of data. Okay, or let's do some genomics. Let's go do something else that is a worthy goal. So you can say, I like that goal. So every time my machine is idle, I want to contribute some CPU cycles to it. Okay. So you can download the client and say, I would like to contribute to that project. Or you can say, I don't mind contributing to any worthy project. So whenever your machine becomes idle, which is going to be a special screensaver that activates, that defines what idle means on your machine. That program is actually not a screensaver, it's a program that's asking for work. And that work involves data processing or some simple compute that you are going to do. Okay, and then you are going to keep doing this until the user comes back, screensaver deactivates, and your machine is back. Okay. So it has the same kind of principles that Sprite had, which is it's your machine. Okay, you decide when you want to contribute it for others, and you take it back when you are back. Okay, yes, question. Okay, another security problem. There are lots of security problems. You don't want to donate your cycles to arbitrary things, then you will soon be doing crypto mining for others, which you shouldn't, right? So yes, I think that you want to trust who you are taking the jobs from. Okay, so you only basically go to reputed projects and say those are the ones I trust. Okay, you don't say I'll take anything anybody wants to send me.
What about the other way around? Like, what if the person who's sending a job is trustworthy?
Right. So there's a great question, which is what if I am the sender, but the machine that donating cycle is malicious? It sends me bogus results. Okay, that is already something that they assume is going to happen. So they are going to take each job and run it n times, and they are going to vote on the results to make sure that malicious nodes are not going to throw your results off. Okay, so every job is going to be run multiple times to make sure the result that you pick for that job is actually going to be accurate. Okay, so even if some fraction of nodes are malicious and sending bogus data, hopefully by replicating it, having redundancy, you are going to be able to catch that. Okay, yes, question there.
So do they always replicate every single job, or is there a way that you can randomize it so that you're not literally putting your competition?
Right. So I think that depends on how critical the job is, how much noise you can accept in your results and whatnot. So those are all parameters you can set, saying my job has n subtasks, each subtask should run 3 times. So you can set all of those things. Right. So that is not necessarily dictated by what you do. I mean that this is a high level idea, you can implement it in many different ways. Okay. Any other questions on volunteer computing? Okay, there is one more I'm going to do and then probably stop. Okay, which is how do these ideas exist today? Distributed scheduling exists on large clusters. Okay, if you have used Swarm or Gypsum, you have a head node. That's your coordinator. Okay, you submit your job to that one node. It keeps track of all the other nodes in the system, which ones have work, which ones have idle. Whenever jobs come in, they join a queue, and from the queue they get scheduled onto some node in the system. Okay, that's how cluster schedulers work. Okay, and if you have actually used any, such as the ones we have in this college, which are Swarm and Gypsum, they work the same way. Okay, so it is now in this case as a centralized coordinator. Okay, it keeps track of how many nodes, not how many nodes, but what nodes are running, how many jobs, what the load is, how much jobs can you send to each node, and so on and so forth. Okay, so that is essentially scheduling in a cluster of servers. Okay. There are also other kinds of systems that people use. One is called Condor, okay, which essentially uses ideas from Sprite. Okay. You can construct a local volunteer computing testbed. Okay. All of you can say, let's become, you download the Condor software and you become part of a virtual cluster. Okay. Every time your machine becomes idle, it can get jobs from your friends. Okay. Every time you want to run more jobs than your machine can handle, you submit it locally, and your friend's machine is idle, it will run there. Okay. It's straightforward to set up these systems using a platform called Condor, which is still an active project from the University of Wisconsin. Okay. So used in large environments where you have lots of workstations that sit idle in the night and whatnot. Okay. People just go home in the night. Okay. Why not use those cycles to run large batch jobs? You got a large cluster that you can create using such nodes. So that's another example. And then there are, of course, we'll come to replicated web servers where you have master nodes and slave nodes when we talk about the web. Okay. So I'm going to talk in 1 minute about Condor and then stop because we're almost out of time. Okay. So Condor uses ideas from Sprite, but it's a system that you can actually run. It's not an operating system, it's a middleware system. It runs on other operating system. It's just a piece of software that you download. It runs like an application. Okay. Essentially, it's going to use idle cycles on machines within a local area network. Okay. It can be used to run batch job simulations. Rather than buying an expensive cluster of servers, you can just take existing laptops and desktops that you already have in your environment and turn it into a virtual cluster, where you are only going to get idle cycles, but you can still use those idle cycles to your benefit. Okay? That's the basic idea. Okay? So idle machine, so there's a Condor coordinator. If your machine becomes idle, okay, it's going to contact the coordinator, send me work. You are going to submit your job to the coordinator. It's going to keep a queue of jobs, whether they're simulations you want to run for your research or some other batch jobs or whatever else it may be. They sit in a queue. Whenever a job becomes idle, you ask, it goes and asks the coordinator, and then it's essentially going to run there. Okay? And the same principle applies. If the user comes back to their machine, job is suspended. Okay? And then you migrate the job. So Condor does support process migration, but it comes with many overheads. Okay? The default in Condor is actually is to terminate the job and try to run it somewhere else. Okay? But if you actually use some advanced features, you can implement the migration features and actually suspend it and resume it somewhere else. That requires homogeneity. Everyone ought to be running Windows, or everyone should be running Linux. You can't mix, you can't transfer a process from one OS to another. That's just too complicated. Okay? So those are all features of Condor, and then there are other platforms like Sun Grid Engine, which is another of this distributed scheduler that does something similar. Okay? So there are many instances of how these early ideas are actually run in today's systems. Okay? And since we are over time, I'm going to stop here. There are 2 slides we'll talk about next time.